Okay, so let's go ahead and move up to the next example. What we want to do here is solve another oblique triangle using the law of sines, and this is another one of those side-side angle or SSA cases. So the first thing we're going to want to do, just like in the previous example, is determine the altitude of the triangle that has these measurements. So the altitude h is going to be the sine of the angle alpha, 35, times the side that's not opposite alpha. That would be b in this case. 230 times sine of, what did we say? Sine of 35 degrees. Okay, you plug this into a calculator. This one, it's going to come out to approximately 76.3. Now you notice A, which is 133, is larger than that amount. So that means that we're not looking at a case where we don't have a possible solution. Notice also that A is less than B. So this is the category of SSA triangle where we can get two possible solutions. So let's start by using the law of sines to get one of those solutions. We have only one angle this time, so I can't find the other angles by making sure everything adds up to 180 quite yet. Instead, what I'm going to do is set up my law of sines with the A and the alpha so that I have sine of 35 degrees over A, which is 133, and set that equal to, let's do sine of beta over B, which is 230. Okay, now beta is the only unknown here. So if I first solve for sine of beta, I multiply the two known quantities, 230 times sine of 35, divide that by the only other known quantity, 133. And then notice, even if I punch this into a calculator right now, I don't have beta. I have sine of beta. But I can get beta by taking an inverse sine of both sides of this. So this tells me that beta is equal to the inverse sine of 230 sine of 35 degrees over 133. Notice I still haven't punched anything into a calculator because this is the stage where I'd want to do that. Everything goes in all at once. In this case, beta is going to come out to approximately 82.7 degrees. Okay, now I have two angles. I have alpha and I have beta. Now I can make sure everything adds up to 180 and find gamma really easily from there. Gamma should equal 180 minus alpha, which is 35 degrees, minus beta, which is 82.7 degrees. If we do the subtraction, I should get 62.3 degrees. 2 down, 1 to go. Now all that's left to do is find C. But with gamma now known, I can use my law of sines to do that. So I would set up my law of sines, which let's use A and alpha since we know exact values for those. Sine of 35 degrees over 133 equals sine of gamma, which even though we have an approximate amount here, it's the best we can do, so we're going to use 62.3 degrees over C. Okay? C then is going to equal 133 sine of 62.3 degrees over sine of 35 degrees. Put that into a calculator and we get approximately 205.3. Now these three measurements make up only one of the possible solutions to our triangle. So I need a second solution. And let's refer back to the diagram showing what this case looks like to see how we get that second solution. Notice, first of all, the first angle that I found here was beta. Okay, so let's come back to this diagram right here. We're talking about this third case right here. Beta is the angle that's opposite side B. What we just found was beta when it's here. Okay, if beta is here, notice that this, from the image you can tell, is an acute angle. We know for certain it's an acute angle because it's one of the non-right angles in this little right triangle right here. Those have to be acute. So this is an acute angle. But the other solution that I'm looking for would put beta right here. And that is an obtuse triangle, or an obtuse angle. Now, come back over here. When I solved for beta, I had to take an inverse sign in that process. That inverse sign cannot give me obtuse angles because of the restrictions that we put on the inverse sine function. Remember, this will only ever give you values in the first or fourth quadrant, but it interprets angles in the fourth quadrant as negative, and for this section, all of the angles are between 0 and 180 degrees, so you never get anything in the fourth quadrant. What that means is that in one of these law of sines problems, this step can only give you angles between 0 and 90 degrees, angles in the first quadrant. That means we have to come up with some other way when trying to get the second solution to this of determining what this angle should be. And the trick to this is to take a look at these two dashed lines right here. If you notice that these two dashed lines together go together with this base here to make an isosceles triangle. Isosceles meaning two sides are the same length. In geometry, we learn that any isosceles triangle, which has congruent sides here and here, will have also congruent base angles. So what that means is that if these two angles are congruent, then, we know that these two angles are congruent. So if I found beta here in my previous case, that's the same number that I would get here. What I want, though, is this angle here. Notice that these two angles add up to 180 degrees because they form a straight line. So if I want to get the beta for my second solution, I have to do 180 degrees minus the beta from my first solution. That's how we get that second solution. So now, if I want to do that here, I'm going to set beta equal to 180 minus, what did we get for beta before? It was 82.7. 82.7. And for this one, we end up with 97.3 degrees. Notice that it's greater than 90 degrees. It's obtuse, which we were expecting. So that is going to give me different values for both gamma and c now. So I have to recalculate those. Now that I know beta, we were given alpha at the very beginning, 35 degrees. I'll get gamma by subtracting both of those from 180. 180 minus alpha, which is 35 degrees, minus the new beta, which is 97.3. And this time for gamma, we get 47.7 degrees. Okay, the last step is to find c. We find it the same way that we did before. Use your law of sines. Sine of 35 degrees over 133. There's sine of alpha over a. Set that equal to sine of gamma, which we have a new gamma now, 47.7 degrees over c. Solve this for c. So I'm going to get c equals 133 times sine of 47.7 degrees all over sine of 35 degrees. And for this case, that goes into a calculator. What we're going to get is approximately 171.5. Okay, together, these measurements and these measurements form the two possible solutions for a triangle that would have these measurements. Let's do one more example for the SSA case. Okay, now this time I want to solve a triangle that has the measurements a equals 20, b equals 10, alpha equals 58. In this case, I could compute h, but there's no need to, because this is the one case that we've encountered where a is actually larger than b. And that was the last case that we saw in the ambiguous case, so the last of those subcases. This will always guarantee one solution with no need to compare anything to h. So I'm going to go straight to my law of sines to start solving. I have a, alpha, and b. That means I should be able to find beta for my law of sines. Sine of alpha, which is 58 degrees, over a, which is 20, equals sine of beta, which we don't know yet, over b, which is 10. Okay? Now, as it was in the previous case, we're going to have to isolate sine of beta and then find beta by taking an inverse sine. I'm going to let you fill in the gaps here. Beta will end up looking like the inverse sine of 10 sine of 58 degrees over 20. This is approximately equal to 25.1 degrees. Okay. Next step, we want gamma. If you have two angles, you can find the third really easily. So gamma is equal to 180 minus alpha, which was 58 degrees, minus beta, which we just found to be 25.1 degrees. This, I'm using an approximately symbol here, only because I know that this is an approximate number, so this will also be an approximation. This one, gamma, comes out to 96.9 degrees. Okay. Last step is to find c. So c comes from the law of sines. I'll use sine of a, alpha over a, so sine of 58 degrees over 20 equals sine of gamma, which we just found to be 96.9 degrees, over c. Cross multiplying, c will equal 20 sine of 96.9 degrees over sine of 58 degrees. And that's going to come out to approximately 23.4. Okay. So that's a few examples of solving oblique triangles using the law of sines. And again, we have those three cases where we can do that: ASA, AAS, and SSA. There's other cases to consider, namely SAS and SSA. Law of sines by itself is not enough to solve those, but we can use something in 10.2 called the law of cosines to do those problems. I want to look at a couple more examples. I'll do this across this video and one more that I'll make after this, where we can use a law of sines in a couple of different applications. So here is a formula for the area of an oblique triangle. It says that the area of an oblique triangle is 1/2 times the product of two sides times the sine of their included angle. So let's see if I can find a picture we've already used for that. Yeah, here's our first page here. So you can see the way that things are labeled. For example, if I wanted to find the height, or sorry, the area of this oblique triangle, if I happen to know any two sides, so A and B, for example, and the angle included between them, gamma in this case, the area would be 1/2 times A times B times the sine of gamma. Now, we will prove this in the next video, but I wanted to state it here so you can see it, and then we'll use it in an example. And then once we're finished with that area example, I have one more law of sines kind of application problem. But we're running out of time in this video, so I'm going to go ahead and save that for the next one.